Welcome everyone to another exciting Wednesday afternoon. You'll have to excuse the little bit of echo from me tonight. I'm Dr. Elena Hyde and I am live from the Alan I. Carswell Observatory at York University. We are in fact live every Wednesday night from 7:30 p.m. bringing you fascinating episodes of TeleTube covering all kinds of different subjects. This night is no different. We have a wonderful broadcast lined up for you about life and habitable planets. So welcome everybody. This is just a reminder, the York Observatory YouTube TeleTube, the online astronomy astrophysics program written and presented by the students, faculty, alumni, and friends of York University. This is Dr. Elena Hyde, and I'm joined tonight by an absolutely wonderful team, Quinton, Sorena, Shannon, Matt, and Abteen, who are going to tell you all about life and habitable planets. We are at the Alan I. Carswell Observatory right now. It is 7:30 p.m. and so that means it is time to start our broadcast. But just in case you are interested or might have missed one of our previous broadcasts, as a reminder, this and all of our shows are recorded on our YouTube channel, so you can always go back and watch them later as well. The York YouTube production works in concert with our regular public viewing and our Monday night York Universe radio broadcast and our Monday night online public viewing. So there's all kinds of ways to get in touch with us. So just getting started here a little bit today. Welcome everybody. I hope you're all having a fabulous Wednesday. And we do have a little bit of a special program lined up for you tonight. Before I start diving into habitable planets and all kinds of other things, there's been a very interesting object in the news recently, most notably Venus. So we're going to be talking about life and habitable planets and what that might mean. Obviously, we can't cover all life in the universe, but we're going to have a little bit of a subset on it. Venus was never thought to be a particularly good place for life, and you'll find out a little bit more about why when our crew presents their findings. But just as a little aside, the discovery of phosphine gas in the clouds of Venus has been, shall we say, a little bit popular in the news right now. Several people have been thinking that it might mean life, but what is life if it is phosphine related? So on Earth, phosphine is created when certain bacteria, which tend to live in very inhospitable places, interact and live. Now, these bacteria on Earth tend to live in places like sewage plants and really nasty environments, and the phosphine itself is said to have a smell kind of like really rotten bad fish. So this particular chemical being associated with a bacteria on Earth is really interesting. But if you look at the paper that came out about the phosphine gas in the cloud decks of Venus, you'll see that actually the scientists are quite skeptical because there are other ways to create phosphine. In particular, phosphine is known to be associated with things like sunlight, lightning, and volcanic activity. And Venus is very hot and does have a lot of volcanoes. So its clouds are not well understood. There's actually a bit of a debate about what kind of lightning might be present in the clouds, whether or not it's possible. We really don't know enough about the clouds of Venus to know if it's biology or if it's an interesting chemical process. Either way, it would be super fascinating to find out. So it is a good thing that this discovery has come up and made people curious about the planet Venus and about its very multi-layered and hazardous clouds. So we're not going to talk too much about phosphine in particular, but we are going to talk about different kinds of potential life, what we know about it, and a little bit of an overview of the situation right now. So phosphine, does phosphine on Venus mean life? Well, I did this survey in my astronomy class earlier today, and they all got it correct. The answers were yes, no, and maybe. So there are all three of those being considered at the moment. And we like to run things by lots of different processes before we make a conclusion. So this means that obviously it would be nice to go and look at these clouds in more detail, see if we can find any bacteria, and if not, maybe we can find chemical processes that produced the phosphine. So it's an interesting mystery, but it's not conclusive. So don't be fooled by articles with big aliens in the front picture. Now, before we get too far away from the solar system and into our full discussion today, I have some wonderful news. As I mentioned before, I am in fact live at the York Observatory, Alan I. Carswell Observatory tonight, which means I can take you to Jupiter. I have a wonderful picture. We are actually able to view Jupiter right now from the telescope here on campus. So let me just go ahead and transfer that over very, very quickly. Hopefully this will look not too messy for you over on YouTube. Okay, now you should all be able to see the Alan I. Carswell 1 meter telescope computer interface. So isn't digital technology wonderful? So let me just go ahead and give you a little tour in case you haven't been here before for our live observations. But the telescope at the Alan I. Carswell Observatory is run through a computer, as are most telescopes. You can see on the left side of the screen, there is a star map that helps us point our 1 meter telescope at the sky. And we have hooked up a brand new camera for you all. We usually use special cameras to do astrophotography in different filters, but we found that wasn't showing good enough images for people over on YouTube and as public viewing. We really wanted to give you that eyepiece experience. So we've actually put a small camera directly up to the eyepiece of the 1 meter telescope. So if you are looking at clear skies right now, you can go outside and look up in the sky. You'll see a very bright star, which is Jupiter, down in the sort of the southeastish direction. It's sort of heading its way across the sky. And Jupiter is a very interesting place. It will come up several times during our talk tonight. So I thought, let's go ahead and have a look. So I'm just going to try to zoom in a little bit here. And as you can see, we have a little bit of color adjustment that needs to happen as well, because we're getting a bit of interference from the haze in the sky. You might have heard of there's a bit of smoke around because of the fires. So because this is a digital camera, I can actually adjust it a little bit to see if I can get a slightly better or slightly worse image out of it. So I'm just adjusting a little bit here to see if I can get some contrast to pop out. Let's see here. And while I'm doing that, since we have the planet Jupiter up here, you'll notice it's not entirely in focus because I have tried to aim for the planet, which means that some of the moons are out of focus. So if you've got very good vision, you might be able to see there's a fuzzy object just to the lower corner inside the screen. That is actually one of the moons of Jupiter. And we will take any guesses in chat as to what moon that might be. Now, I'm just calling out real quick. I believe one of our student presenters, Quinton, you have a little bit to add about Jupiter?
Well, less prominent than Saturn. Jupiter also has rings. Also, astronomers call Jupiter a failed star. So while it's true that Jupiter, like a star, is rich in hydrogen and helium, Jupiter does not have nearly enough mass to trigger a fusion reaction at its core.
That is super fun and very true. It will be very relevant for our discussions of life later on, about what kinds of things might be needed in terms of, well, do you need a star to have life, or could you just have it with a planet? Maybe there's a free floating Jupiter out there somewhere, which has some sort of moons around it that are icy, as you will hear some of the moons of Jupiter have liquid water. So it's quite fun. Now, I'm just going to try to adjust this a little bit. Now, let's see here. I believe one of our other students also has a little bit about Jupiter they'd like to add. Abteen?
Yeah, so Jupiter is, as we know, the biggest planet in our solar system. And the crazy thing with Jupiter is because it's so close to the asteroid belt, it actually captures moons and lets them go at a remarkable rate. So every year when we look up at Jupiter and count its moons, they do tend to change. So watch this space.
Indeed, and I've just adjusted the settings on the image a little bit. As you can see, if I zoom out and increase the brightness of the image that I allowed to come through the eyepiece, you can make out the moons now here on the sides. Now, the moons of Jupiter, I'm not going to give too much of a spoiler alert, but they're all super interesting. You've got the 4 major Galilean moons and something like 70 to 80 other little moons, depending on who you talk to. The Galilean moons, those are the ones with water. You have Europa, you have Ganymede, you have Callisto. There's talk of oceans of liquid water underneath the surface of these moons. In particular, Europa and Ganymede have been heavily featured in science fiction because of the amount of liquid water that they have. Liquid water is very unusual, and it will come up as one of the things we're going to think about discussing when we look at life and all kinds of stuff. So this is up in the sky for you to view tonight. If you have a 1 meter telescope, you can get this view. Actually, you all do have a 1 meter telescope, and this is all yours. So let me just go ahead and readjust the defaults here and get back to our main image of Jupiter. And just so you can see what I'm doing here a little bit, I'm adjusting things like the exposure time, because we have a camera on the eyepiece. It's a little bit like being able to adjust how long your eye would be able to look at the image. Looks like we are getting a little bit of haze popping through, unfortunately, right now. So I wanted to make sure that I showed you Jupiter as much as I could while we had it, and that looks like it was a good strategy. So we are seeing a bit of fuzzy haze. That is actually smoke from the fires on the West Coast coming through. Very sad, but best of luck to everybody over there. And I'll just adjust a little bit more here. As you can see, it's always a bit of an art form with telescopes. If we were taking scientific images of Jupiter, we would be taking these one by one in different filters and then combining them. All right. There we go. Looks like our little patch of haze has cleared a bit. So we now have again the rings of Jupiter, and it is worth noting that the entire planet Earth would fit within a fraction of this ring. So I don't know if you can see the little hand cursor I have on the screen in the 1 meter, but that is much, much larger. I believe that's got to be like 4 or 5 Earths across already. Jupiter is much, much larger than Earth, and its bands are of clouds. It is a gas giant planet. So these clouds are interesting for our conversation with Venus, because finding phosphine in the atmosphere of Venus, we think it might be linked to bacteria or chemical activity that we don't yet understand. But it was Carl Sagan who originally proposed that there could even be life in the clouds of Jupiter. So it is a very interesting place here. And I'll just go ahead and open it up from any of our crew if they'd like to add an extra fun comment about the planet Jupiter.
I'll add one thing about Jupiter that I like is when sometimes you see the Galilean moons will project their shadow onto Jupiter. It's a very cool sight to see. And that also happens to occur on Saturn with its moon Titan. So if you catch it at the right time, you'll see the shadow of their moons project onto the planet. And it's very cool to see. And throughout a period of time during the night, the shadow will shift off. It'll slowly move and shift off. It's just cool to see.
Oh yeah, and it is worth noting that Jupiter spins quite quickly, and the rotation of its moons means that you personally could watch. If we sat and watched, we would eventually be able to see these moons go past. So of course we have delayed our start a little bit by about 15 minutes to show you these wonderful live images, but I am going to go ahead and start our regular program now. If it's still clear and not hazy, I will try again at the end of the show if there's time. But thank you for joining this little bit of live images. So we're just going to shift over and start talking about what we were originally going to talk about, life and habitable planets. So as far as we know, Jupiter is not habitable to us. Its moons are a bit of a debate. Venus is definitely not habitable to us, but its clouds are very, very interesting. So I'm going to go ahead and start off with Quinton. Quinton, can you go ahead and give us our official intro for today's talk?
Good evening, everyone. I'm Quinton, and I'm here with Sorena, Shannon, Matt, and Abteen. And we're here from the Alan I. Carswell Observatory at York University. Tonight, we've got a great presentation about life and habitable planets. The planet Earth is teeming with life of all varieties. There are an estimated 1 trillion extant species of life on Earth today, an amount that makes up less than 1% of the total number that have called this planet home across all of history. From the deepest depths of the ocean to the driest deserts, life has adapted to survive in every environment this planet has to offer, no matter how harsh. But what about beyond our planet? Could there be life elsewhere in the universe? What features must a body have in order to support living organisms? This is a question that has fascinated and perplexed scientists for centuries. Before we discuss the results of these inquiries, let's delve into the history of the question itself. During the Renaissance, the work of scientists such as Copernicus, Kepler, and Galileo slowly led to more widespread acceptance of the idea that the Earth was not at the center of the universe. Around this time, Galileo was able to observe that Jupiter, like Earth, had its own moons. All of these discoveries caused many astronomers to adopt an attitude that there was nothing particularly special about Earth or its place in the cosmos, and that the universe could be full of countless other bodies that were similarly full of life. One of the early proponents of this idea was the Italian philosopher Giordano Bruno, who in the 16th century hypothesized that every star in the universe had its own planetary system, with these other worlds having no less virtue nor a nature different to that of our Earth, and containing animals and inhabitants, just as the Earth does. The idea of life on other planets continued to be popular in fiction and philosophy for centuries to come, with writers speculating about the possibility of life on all the bodies in the solar system, including the sun and moon. But eventually, one planet would grow to occupy the position of greatest prominence in the domain of speculative alien fiction: Mars. Scientific and cultural interest in the possibility of life on other planets grew in the late 1800s, when the astronomer Giovanni Schiaparelli reported being able to see canals on the surface of Mars through his telescope. The topic of intelligent life on the red planet was met with skepticism by most astronomers, but the idea utterly enthralled the public. We are now extremely confident, however, that there are no civilizations on Mars. While it's true that science and science fiction have given us many ideas about life in the universe over the years, few thought experiments have proved as exciting as the Drake equation. The Drake equation, also known as the equation with no solution, is meant as a thought experiment to help astronomers estimate how much life might be in the universe. It was first written in 1961 by Frank Drake as a way to stimulate dialogue at the first scientific meeting on the search for extraterrestrial intelligence, SETI. SETI, by the way, is now famous for its ongoing search for lifelike radio signals. The Drake equation was meant to provide a list of concepts to contemplate when considering the question of other radio communicative life. With the Drake equation, scientists try to solve for n, the number of civilizations in the Milky Way galaxy whose electromagnetic emissions are detectable. The factors that are under consideration are R star, the rate of formation of stars suitable for the development of intelligent life, FP, the fraction of those stars with planetary systems, NE, the number of planets per solar system with an environment suitable for life, FL, the fraction of suitable planets on which life actually appears, Fi, the fraction of life-bearing planets on which intelligent life emerges, FC, the fraction of civilizations that develop a technology that releases detectable signs of their existence into space, and L, the length of time such civilizations release these detectable signals. As you can well imagine, many of these are quantities that will never be exactly known, which is why the Drake equation is said to have no solution. That said, we do regularly experiment with these values based on our current understanding and use the estimates of n to start discussions about life in the universe. A current optimistic setting of the Drake equation would place 756 civilizations in our own Milky Way galaxy. Drake himself came up with an estimate of 10. How many do you think there are?
And we'll just hop over. I'm seeing a few comments in chat on estimates. I currently go with 42 is my favorite number for the number of civilizations. Anyone else have a favorite number of civilizations that they'd like to vote for? I suppose 42 is kind of an easy one because we talked about science and science fiction colliding, the Hitchhiker's Guide to the Galaxy and the answer to everything. So if you get a Drake equation to play with, for example, on your computer or whatever you like, however you like to do math, you can get the answer of 42 a number of different ways, which is kind of a fun game to play if you like to take your science not too seriously. We have one vote of infinite number because we may never know, which is actually a very good point coming up in chat right now. And of course, any number that you think, we could probably get that from the Drake equation. All right, thanks, Quinton. I'll let you go ahead and tell us a little bit more about the background here.
In addition to scanning the skies for evidence of communications with SETI and other programs, humanity has also attempted to send out certain messages of our own, such as the radio frequency Arecibo transmission of 1974, and the golden records included on the 2 Voyager missions in 1977, both of which contained basic information about humanity and Earth. Since the 90s, as telescope technology has continued to improve, astronomers have begun to devote more attention to the discovery of exoplanets orbiting distant stars. To date, astronomers have discovered around 50 exoplanets that may be within their star's habitable zone, some of which, such as Kepler 452b, have entire observatories dedicated to scanning them for radio transmissions. Additionally, the search for fossils, microorganisms, and organic carbon has been a priority of NASA's Mars rover missions since 2016. This has been a brief history of life thinking about life, but it pales in comparison to the history of life itself. For a bit more background on how life emerged on this planet, I'm going to hand the mic over to Sorena.
Thank you, Quinton, for educating us on the fascinating history of humanity's thoughts and ideas regarding the subject of life and habitable planets. Now, I would like to discuss the early Earth before exploring the origins of life on the planet. The planet Earth was formed about 4.54 billion years ago, about a third of the universe's age, in the accretion disk surrounding the solar nebula. The process of forming the planet Earth was conducted from an accumulation of particles in the solar nebula's accretion disk, which gravitationally attracted more gas and solid matter, eventually evolving into a more massive object. During this period of our solar system, there were frequent collisions with other with other bodies, which resulted in the Earth being molten and with intense volcanic activity. Volcanic outgassing likely created Earth's primordial atmosphere, which contained almost no oxygen, then subsequently formed the early ocean. During this period of early Earth, a planet-sized body is thought to have impacted Earth, taking off a large proportion of its matter into orbit around the young planet, forming the Moon. The Earth began to cool over time, allowing its solid crust to form. 4.28 billion years ago is when the first life forms are thought to have appeared on Earth. The specific mechanisms by which life initially developed on Earth are not well understood, but it is generally agreed upon that certain organic molecules such as amino acids must first form out of simpler compounds. Experiments have demonstrated that it is possible for such chemicals to be created in an environment rich with ammonia, methane, water, and hydrogen, which were all present on Earth in large quantities at this time. While life on Earth is believed to be over 4 billion years old, Earth's atmosphere did not contain significant amounts of oxygen until 2 to 2.4 billion years ago. For nearly half of its existence, life on Earth was entirely anaerobic, meaning it did not require oxygen for growth. It is believed that the early Earth's atmosphere consisted primarily of nitrogen, carbon dioxide, and noble gases. During the earliest phases of life on Earth, it is thought that the sun only output about 70% of the energy that it does now, which in theory would not be enough to even sustain liquid water, let alone life. The fact that early Earth possessed both is known as the faint young sun paradox. One possible solution to this is the greenhouse effect in the early atmosphere. It is still debated, but no matter what you think of the sun, it is clear from the geological record that photosynthesizing cyanobacteria were able to emerge gradually and increase the oxygen content of the atmosphere over time. This allowed organisms that made use of the process of aerobic metabolism to thrive where previously no such possibility existed. And since aerobic metabolism is 15 times more efficient than anaerobic metabolism, an explosion of complexity ensued. In the oxygen-poor atmosphere the Earth had sustained for billions of years previously, life would have struggled to even reach multicellularity. Even animals, plants, and fungus on Earth today owe their existence to this explosion of oxygen 2 billion years ago. But we shouldn't fool ourselves into thinking that the Earth was barren like a desert before this. The early Earth shows us that a planet devoid of oxygen can still be teeming with life. Titan is the largest moon of Saturn and is the second largest planetary satellite in the solar system after Jupiter's moon Ganymede. Both objects are actually larger than the planet Mercury. Titan is also special for another reason. It is the only moon in our solar system to have its own dense atmosphere, and the only other solar system object that is known to possess stable bodies of surface liquid. Much like the early and present-day Earth, Titan's atmosphere consisted primarily of nitrogen, and it also contains significant quantities of hydrocarbons such as methane. In fact, Titan is believed to be rich in complex organic compounds, and in many ways, its atmosphere is similar to the composition to that of the early Earth's. As mentioned previously, it is probable that there are even lakes and seas on Titan's surface, although these would be composed of liquid methane and ethane as opposed to water. The lack of surface water is one of the major differences between Titan and the early Earth, and this scarcity of water extends to its atmosphere as well. Water vapor is the main chemical present in the early Earth's atmosphere, but absent from Titan's. However, it is possible that this dearth of water might not matter as much as one might expect. In 2010, the planetary research team from the University of Arizona showed that the amino acids and the nucleotides bases that comprise DNA and RNA can still form in an environment similar to Titan's atmosphere. This is the first time such an experiment was able to succeed without the presence of liquid water. When astronomers talk about the search for other bodies that can support life, often we assume that this means we need to find objects that are similar to Earth as it exists now. It makes sense that we might jump to conclusions. After all, the modern Earth is the only one that humans have ever experienced. And any object that differs too much from the modern Earth would be very hard for humans to live on. One criteria often used is the size of Earth. And towards that end, the NASA's Kepler mission exists to search for Earth-sized exoplanets. As mentioned before by Quinton, the number of planets suitable for life is an important metric in determining life in the universe. Since Earth-sized planets are small and hard to find, these initial Earth-sized planets around the sun, like stars, are exceedingly rare. However, as we know from our neighbor Venus, being close to Earth size might not be enough. But if we expand our definition of the word Earth-like to take into account what our planet was like for billions of years before we got here, it becomes clear just how good the odds are that life could exist elsewhere. An object doesn't need oxygen to be Earth-like. Earth itself had barely any oxygen for millennia after life first emerged here. An object doesn't need to orbit a star like the modern sun to support life either. Our sun was very different 4 billion years ago, but life sprung up anyway. An object doesn't need liquid water to mimic the conditions of the early Earth. In fact, as Titan has shown us, such an object doesn't even need to be a planet. We already know that life can emerge on worlds that are drastically different from ones that we live in. We know this because it already happened. But maybe we're getting ahead of ourselves. We've been contrasting the early Earth with the modern Earth, but we never really explained what it actually is about the modern Earth that allows life as we know it to flourish here. And it is possible for life to emerge in an environment completely different than that of our planet. At any stage in history, these and other questions will be answered by Shannon in the next section.
Thank you for Sorena for explaining the early Earth and the current Earth. But there are a few more questions I would like to explore. These questions are, what makes the Earth habitable? What is the difference between Earth, Venus, and Mars? And could life actually exist on planets that aren't like Earth? There are a few things that we know of that make Earth a nice place to live. Firstly, the moon. The moon does a lot more than we think it does. In fact, it's even thought to have a stabilizing effect on the Earth's orbit. In addition, the moon also contributes to the tides, and some biologists actually believe that it may actually have begun in tidal pods. Secondly, stable rotation. Our Earth rotates, which allows for there to be a climate regulation through the changing of night and day. The frequency of night and day helps prevent extreme temperatures, and this allows for there to actually be a progression of life. Thirdly, dynamic geology. Eventually, when the cloud of gas and dust came together to form into the Earth, it actually contained enough radioactive elements, which helped to keep the core of the Earth stirring for the past billions of years. This motion is the reason why we have a magnetic field to begin with. Earth has a strong magnetic field. Our magnetic field protects from the harsh cosmic rays and solar flares that would otherwise fry our planet. Next, the atmosphere. The atmosphere includes the gaseous part of the Earth, all the way from the surface to gradually merging into space. This ozone layer absorbs the majority of the ultraviolet radiation from the sun. This allows for there to be a protective layer between us and the harmful rays of the sun. The importance of the ozone layer is the reason why so many people are worried that it will be destroyed due to human activity. The ozone layer allows for life on Earth, and without it, humans would not be able to live on Earth. Lastly, the Earth's location, the habitable zone. Earth is located in the habitable zone known as Goldilocks zone. It is due to our location that we're able to live on Earth. The temperature is just right, and it allows for there to be liquid water to exist on Earth. You can see a diagram of this on the slide. Named after the Roman god of war, this popular red planet has always been the topic of terrorists on whether or not life resides on it. Mars is the fourth planet from the sun, which is 128 to 155 million miles from the sun, has a diameter of 4,222 miles, which means it's a lot smaller than Earth, which has a diameter of 7,926 miles and has a density of 3.9 grams per centimeter cubed. Currently, no humans have had a journey on Mars, and NASA has been actively searching for life on Mars. Although Mars may appear a little bit similar to Earth, it's still very different from Earth. Unlike Earth, Mars has no liquid water on its surface and is actually covered in rock and dust. Rather, the water is ice. The main reason why it is unlikely that there's life on Mars and it's uninhabitable is due to the fact that unlike Earth, Mars has no magnetic field and much less air than Earth, which means that a lot of harmful space radiation reaches Mars' surface. Amazingly, scientists continue to research whether or not there was once upon a time life on Mars, as they continue to search for fossils of tiny organisms that did not evolve over time. Venus, named after the Roman goddess of love and beauty, this hot planet is the closest in size to Earth. Earth takes 24 hours to rotate. Meanwhile, Venus takes 225 days, which means that a Venus year is actually less than a full day on Venus. Venus's atmosphere is 90 times more dense than on Earth, and is made of a majority carbon dioxide, which is 96.5%, and 3% of it is nitrogen. Due to the denser atmosphere and the chemical composition of Venus, means that Venus experiences a great greenhouse effect, which causes the temperature of the surface to more than 470 degrees Celsius, which means it's uninhabitable by humans. But what if life could, in such high temperatures, actually live? Or in the clouds, as we discussed in the beginning of the show. Venus is covered in clouds that are made of sulfuric acid droplets, which are very reflective. This makes Venus the most reflecting body in the solar system. Earth is all that we know, and we know that life can reside on Earth. But what if there's life out there that doesn't need any Earth-like environment? We adapted over a very long time to exist on Earth. So although these extreme environments may be unfit for us, they might not be for other beings. This is the idea that is so fascinating for me, because as we search for planets that resemble Earth, there may be planets that are completely different to Earth, but still contain life, maybe even an intelligent life. Europa is not very similar to Earth. It's a moon. More specifically, Europa is the fourth largest moon of Jupiter, and Europa could have a possible subglacial water ocean, which means it could be possible for human life to live either on or below the surface. There's water in Europa, which means there could be life. Even on Earth, there are organisms that can survive in extreme environments that no one would expect be able to sustain life. These organisms are called extremophiles and can survive in extreme environments such as intense heat, extreme pressures, extremely cold temperatures, and highly acidic environments. Therefore, there could be extremophiles on a whole ton of planets. So when we think if a planet is habitable, do we mean is it habitable for humans or habitable for extremophiles? Astronomers continue to search for life in the universe, but how? Matt will let you know.
Well, thank you, Shannon, for your explanation. And yes, while the possibility of simple life forms existing elsewhere in our solar system is still being investigated by astronomers, we have to come to the consensus that if we want to find intelligent life, we might need to search elsewhere. One of the first proposals for scanning the cosmos at large for extraterrestrial radio signals was made in 1955 by John D. Cross and was approved by Ohio State University within 2 years. The resulting radio telescope, the Big Ear, became one of the first long-term attempts to search for extraterrestrial intelligence, and it was till this day the longest-running SETI project before it was demolished. Nowadays, there are more than 160 active radio telescopes across the globe. And well, the Ohio State University's Big Ear Radio Telescope became famous worldwide after 1977, when the volunteer astronomer Jerry R. Eman discovered an anomaly in the recordings of the radio transmissions the telescope had been receiving. It appeared as a radio signal with great intensity and different frequency from the rest of the other signals coming from the direction of the constellation Sagittarius. It lasted more than 72 seconds. Now, the origin of these signals still causes some debate among the scientific community. There are researchers like Dr. Antonio Paris who believe they may have found a plausible explanation for the signal, saying it was the radio waves emitted by two comets passing through a hydrogen cloud. But some still dismiss this explanation since the comets that Dr. Paris mentioned were not there at the specific time the event occurred, and the frequency emitted by the signal was not at all the type of frequency that is usually produced by a comet. So, do you think this was a signal from intelligent life trying to communicate with us, or was this only a comet passing by? We'll leave this for you to make some research about it and help us in the quest for the true explanation for the wow signal. And it is in the same year that we also start our quest to not only find life, but to tell the universe we're here. On August 20th and September 5th of 1977, Voyager 2 and Voyager 1 were launched respectively with the purpose of studying the Jovian planets. It was, according to NASA, a once-in-a-lifetime opportunity since four of the planets, Jupiter, Saturn, Neptune, and Uranus, were going to be aligned, and this wouldn't happen in another 176 years. The important feature for today's topic that both of these probes have is the Voyager Golden Record, which, greetings in 55 ancient and modern languages, more than 115 images and recordings of sounds produced by nature and humans, human anatomy, the solar system, and our location in it compared to the nearest pulsars, as well as some scientific data, physical and mathematical quantities, and the hydrogen atom are contained in this record. After more than 40 years, both Voyagers are still sending us information about their surroundings, but sadly, no contact with another intelligent organism has been made yet. Another important attempt is the Arecibo message, as previously mentioned by Quinton, which was our first interstellar radio message. It was sent in 1974 from the Arecibo telescope in Puerto Rico. It consisted of a pictorial message containing information about our planet and humanity, our nature, as well as our location. As you can see on the picture, there's a brief explanation of what the message contained. In the upper part of the message, we can see one thing that can be considered as part of, a universal language, we could say, which are the numbers from 1 to 10. And after that, we have the atomic numbers for hydrogen, carbon, oxygen, and phosphorus, which are known as key elements for the existence of life. After that, we can see 8 different figures which symbolize the structure for sugars and bases contained in our DNA. Then we can clearly notice the double helix structure of our DNA, and below it the shape of a human, as well as an average height and human population at that time, which was 4.3 billion. Last but not least, we can see our solar system with the Earth displaced upward to show where the message was being sent from, and a figure of the Arecibo transmitter with the diameter of its dish. And this transmission was sent towards the star cluster M13, which is located more than 21,000 light years away from us. And it had 1,679 binary digits, and it lasted more than 3 minutes long. And well, we've put a lot of effort actually into trying to find signs of intelligent life, but so far we haven't found any. That's why up next is Abteen to provide some possible explanations of why that might be.
Wow, awesome. Thank you, Matt, for telling us all about the research and findings. We've been listening for signs of life, such as the wow signal, and been sending signals of our own out into space, such as the Arecibo message. As Quinton told us earlier, some estimates of the solution to the Drake equation yield hundreds of civilizations in our own Milky Way. Yet this begs the question, why have we not found any other life forms yet? This question has been asked for many decades. This paradox is named after the Italian physicist Enrico Fermi, and as you may have heard before, it's been dubbed the Fermi paradox. The idea is, if we are a part of a relatively young planetary system compared to the rest of the universe, the Earth should have already been visited by aliens. So, where are they? We try to explore a few of the many possible solutions tonight. Fermi realized that any civilization with a modest amount of rocket technology and an immodest amount of imperial incentive could rapidly colonize the entire galaxy. Within 10 million years, every star system could be brought under the wing of the empire. 10 million years may sound long, but in fact, it's quite short compared with the age of the galaxy, which is roughly 10,000 million years. Colonization of the Milky Way should be a quick exercise. If we should choose to believe that aliens exist for the sake of finding explanations, we have some options. One possible explanation is a simple one. Aliens simply chose to never come to Earth. Another explanation has to do with the sheer difficulty in space travel. This could be biological difficulty, since space is a very hostile environment to be in, at least for us humans. It could be engineering difficulty, since it is quite difficult to simply get out of a planet's gravitational field, let alone the host star's gravitational field. Or it could be astronomical difficulty. It is also very difficult to find exoplanets, and although we humans have been successful at finding them, we have yet to find one with promising signs of life. In 1980, Frank Tipler, a professor of physics at Tulane University, followed up on the Fermi paradox with a paper titled "Extraterrestrial Intelligent Beings Do Not Exist," which was published in the RAS, or Royal Astronomical Society's quarterly journal. The bulk of his paper dealt with how to get resources for interstellar travel, which he suggested could be achieved by having some kind of self-replicating artificial intelligence moving from star system to star system and creating copies using the material there. Well, since such beings are not here on Earth, Tipler argued that we are very likely the only intelligence in the universe. There is another idea as well, the astronomical number of planets and the vastness of space. As we know, the universe is incredibly vast and old. Some estimates indicate that although the universe is roughly 13.7 billion years old, its diameter spans 92 billion light years, and it's growing faster and faster. If aliens existed, it would be incredibly difficult for them to hop galaxies, so perhaps we should look closer to home. Or perhaps home is special. In 2015, a study looked at the likelihood of a world evolving with a habitable environment using data from the Hubble Space Telescope and Kepler Space Telescope. It suggests Earth was an early bloomer. The study suggests that our planet's birth came very early in the universe's history. When Earth was formed about 4.6 billion years ago, the study said only 8% of the potentially habitable planets that will ever form in the universe existed. In other words, most of the material available to form habitable planets is still around, giving lots of time for alien civilizations to form. Finally, it could also be more about life itself. As Shannon told us earlier, life can take on many other forms different than our own. Perhaps life is too fragile to survive for long periods of time. In 2016, a study suggested that the early part of a rocky planet's history, like Earth's, can be very conducive to life, as life could emerge after about 500 million years after the planet cools down and water is available. On Earth, it was about 770 million years, so a little bit longer. However, after that point, the planet's climate could easily wipe life out. A good example is Venus, which has a runaway greenhouse effect, and another, Mars, which lost most of its atmosphere to space. There are many more theories as to why we have yet to interact with aliens. If you're interested to find out more, ask us in the chat now, or feel free to chat with us on Mondays during our online public viewing.
All right, everyone, we do have a little bit of a chance. As you know, this episode is going a bit longer due to the live observing at the observatory right now. I actually have a chance to maneuver over to Saturn if I can get the dome to cooperate. So I'm just going to have Abteen entertain you with our official outro while I walk over and adjust the dome.
Fantastic. We look forward to seeing the live pictures of Saturn through our beautiful 1-meter telescope. Well, everyone, you have been listening to the Alan I. Carswell Observatory's weekly TeleTube broadcast, the astronomy and astrophysics program written and presented by the students, faculty, alumni, and friends of York University. The hosts this evening have been Quinton, Shannon, Sorena, Matt, and me. Make sure to leave any comments or questions in the comment section of the video. You can always connect with us on Twitter with the handle @York Observatory, and check out our website for show notes, content, updates, and contact info at observatory.info.yorku.ca. You will see all of the pertinent information on your screen. Thank you for tuning in. Clear skies and have a great night.
All right, and just while we are taking our images here, we will take questions in chat, and if I can't get the image to pop up because of clouds, I'll just crop this out later. All right, a little bit of success. I am sorry to report I have lost my connection to our fancy camera just for Saturn, but for those of you still hanging around in chat for one more planetary view, I'm happy to show you Saturn tonight. So I'm just going to increase the image size here for you. And as you can see, we can view Saturn through the 1-meter telescope, and some of those interesting moons you may have heard about today with their crazy atmospheres and all kinds of interesting properties. So let me just go ahead and do some adjusting on this. As you can see, we can clearly make out the rings of Saturn despite the haze. It is a wonderful view tonight, live for you from the 1-meter telescope here at the Alan I. Carswell Observatory. I'm just going to adjust the view a little bit. And I believe we covered the moons of Saturn a little bit, especially the one with atmosphere. But Saturn's rings are also quite interesting because we think that they are made of a lot of ice and little rocky particles. The way that the rings are spread out, it might have been an object that got too close to Saturn and broke up to form those rings that we see so brilliantly. And actually, if you could squish all the rings down, it would only be the size of, your average medium-sized moon. So the fact that they're spread out like this now is a little bit of a lucky coincidence for us that we are sort of at the point of evolution in Saturn's history where we're able to see them. And given enough time, it is entirely possible that the rings will dissipate or recombine into a new moon. All right, as you can see, we have a little bit of haze on Saturn, but you can just make out through our 1-meter telescope that there is a bit of a shadow. That's Saturn casting a shadow on the rings behind it, blocking the backside of the rings from our view. So we can make out a little bit of the shadow of Saturn on the rings as well. So thank you everybody for joining our wonderful broadcast. It is almost time to stop, so we will take questions for about the next 3 minutes over in chat, and I will leave this lovely picture of Saturn up for you all. All right, everyone. Thanks again for joining the Alan I. Carswell Wednesday night TeleTube. This is time for us to end our broadcast. But if you are staying up late tonight, make sure to look uppity, as they say. It's not just Jupiter and Saturn, but Mars will be rising later on as well. The moon is pretty much new, so there's not a lot to see there at the moment. But, there's quite a few good shows going on from our other planets. We hope you have a wonderful evening, and this is our Wednesday night broadcast signing off.